In cinema, a sword behaves like a weightless laser, capable of slicing through stone and steel with zero resistance to the blade's edge. On a real battlefield, that steel is a long, vibrating lever. Upon impact, thousands of pounds of kinetic force ripple through the metal's grain. That trauma occurs every time a blade is driven into a wooden barricade, caught in the links of steel chainmail, or slammed into a dense human bone. Under these loads, steel reaches its elastic limit. If the physics are wrong, the weapon will fail in one of three ways. The metal will shatter, the blade will permanently warp, or the edge will roll and lose its geometry. To prevent these structural failures, a smith must balance three competing variables: hardness, flexibility, and edge geometry. Hardness is the first requirement. A heavy weapon like a Katzbalger or a Scottish claymore must be hard enough to resist denting when it strikes a solid oak shield or a steel breastplate. This image shows a blacksmith's forge. By using intense coal fires to reach critical temperatures, smiths can alter the carbon structure of the steel to achieve that necessary hardness. However, hardening is a metallurgical trap. The harder the steel becomes, the more brittle it gets, making the entire structure vulnerable to shock. We saw the result of an over-hardened blade with Jonathan's claymore. When the sword struck a dense target, likely hitting the spine, the brittle steel could not flex to absorb the energy. It exploded into fragments. Without the ability to deform slightly under pressure, a perfectly hard blade is functionally useless. The strength that makes it cut also makes it shatter. To counter brittleness, smiths temper the steel, trading some hardness for flexibility, so the blade can absorb an impact and return to its original shape. The Indian patat represents the extreme of this engineering. Its gauntlet-mounted blade is often so flexible it can bend 20 degrees in either direction without taking a permanent set. But too much flexibility creates a different failure state. During a carcass test, Matt's claymore was so springy that it couldn't bite into the target, essentially bouncing off the surface. When a blade is too soft, the strike's force reverses into the wobbly steel, causing it to whip. A properly tempered blade remains rigid. The kinetic vector continues through the steel, driving deep into the target. A weapon that survives the strike but fails to transfer its energy has effectively failed as a tool of combat. Assuming the metal's internal properties are balanced, lethality then depends on edge geometry, the specific cross-section and shape of the blade. This image shows a cutlass. Its forward-heavy, broad geometry is built for hacking. It creates a wedge-like effect designed to shear through thick naval ropes and wooden barricades in tight spaces. Compare that to the Indian talwar. Its deep curve is optimized for a draw cut, allowing the edge to slide across flesh and lacerate deeply without snagging on the underlying bone. Here we see several Indian weapons, focusing on the katar on the far right. Its H-shaped handle aligns the blade's geometry directly over the bones of the forearm, maximizing the force delivered in a straight thrust. If this geometry is off by a fraction, the weapon's utility vanishes. A poorly angled edge will skate off a target or roll over instantly upon hitting a hard surface. These shapes were never aesthetic choices. They were precise responses to the specific armor and obstacles of their era. A historical sword is not a mythological artifact, but a compromise between the competing laws of metallurgy and motion. A chakram gliding on a precise aerodynamic plane, or a schiavona cleaving a target, are the visible results of these variables working in total alignment. Behind the romantic legends of these blades lies a brutal scientific reality. A smith had to understand exactly how much trauma a thin piece of steel could endure before it reached its breaking point. By calculating that narrow margin between hardness and flexibility, these ancient engineers provided the razor-thin difference between a failing weapon and a warrior surviving.